generally talk about multi-step mechanisms, called electrochemical mechanisms. And I better not use EC as an abbreviation for electrochemical, I better just write it. Because EC is going to be a very specific kind of mechanism. Okay, so a single step mechanism might be O plus an electron going to R, right? And this is what we have been talking about. But imagine some species, say you do an electron transfer to some species, and say you start with a alkyl halide or aryl halide, some hydrocarbon, and I put an extra electron on that hydrocarbon. All sorts of things could happen, right? If you're an organic chemist, that's a very reactive species, right? So it can go through all sorts of chemistry. So I'm going to make basically RX radical, right? And this thing can do all sorts of things. But it could react with itself to make a dimer, right? It could undergo a second electron transfer to make a doubly reduced species that perhaps is more stable, right? So methylbiologen, right? You can do 2 reductions on methylbiologen. It could dissociate. It could cleave this RX bond, right? It could cleave that bond if that was a stable reaction pathway, if this radical was sufficiently unstable. It can react with an electrophile in solution, right? You have an electron here, a radical. So it's a sort of nucleophilic attack on an electrophile, right? So you can imagine all sorts of chemical reactions that might happen, or electrochemical reactions that might happen. And so it's important in the context of understanding electrochemistry to think a little bit and classify how these types of reactions occur. And what we'll do is we'll just talk about something simple. This is called an EC reaction, where you have an electron transfer step followed by a chemical step. Okay? Reaction is an electron transfer reaction followed by a chemical step. We can also have a CE reaction, which is a chemical reaction followed by electron transfer. So more generally, we're going to call an E an electron transfer, and a C a chemical step. Right? And so we can put these together in various ways. We can have EC, we can have a CE, we can have a ECE. We can have all these different steps, and that's a way to classify the mechanism underlying an overall electrochemical transformation. Let's do a CE reaction. Okay? That's a chemical step followed by an electron transfer step. So imagine we have some species Y in equilibrium with O. So this O can react with electrons to give you R. Right? So what's the chemical step here?
Y. Y goes to O.
Right?
Yeah.
And this is the E step, the electron transfer step. So the availability of O, right, is going to depend on this pre-equilibrium, so-called chemical pre-equilibrium. You see this a lot. The thing you actually react is not the thing that you put in the electrolyte. For example, imagine Y had to absorb on the electrode surface before it could react. Then there'd be some pre-equilibrium governing how much of the Y is actually absorbed on the electrode surface where it can do the electron transfer. So that would be an example of a CE reaction. Okay. So another example might be in the organic chemical context. You have this diol here, which is going to be in equilibrium with an aldehyde form. Plus water. And this, you know, you can reducible easily, and this one is non-reducible. Okay? So depending on the equilibrium constant for this equilibria, you will modify how much O you have available that can be reduced to R. So let's think about now the other class of reaction, an EC reaction. And I think actually in that J. Chemed article from Gillian Dempsey's group at UNC, they talk about some of this stuff, right? Yeah. We'll see, maybe I'll get there. So imagine O plus N electrons going to R, followed by R with some rate going to X. Okay? So here's another example, right? So you make R, but R has some following chemical reaction where it can make species X, and species X is non-electroactive, meaning X you can't oxidize back to O. Right? And there's going to be some rate constant here. So let's think about this. What happens if Kf is large and much, much greater than Kb? What's the CV going to look like? So let's start first with a perfectly reversible, right? So if I have a perfectly reversible reaction, okay, this would be Nernstian. Okay, that you kind of learned about. Now, what would happen if this reaction, if Kf is large, so it's kind of, the reaction is fast on the time scale of taking this voltammogram, and Kf is much bigger than Kb. So once it goes this, it doesn't come back easily. What's going to happen to that voltammogram?
You won't see the lower part.
You won't see the lower part, right? So you'll see, well, this is, we'll keep it easy. So I is going to be, I'll do it in Texas convention. Negative, positive, negative, positive. Keep switching back and forth. I apologize for that. So, you know, you'll see this part, right? But you won't be able to reduce it back. And you see this a lot. If you are an organic synthetic chemist, this is called irreversible, in this case, a reduction, or you might see irreversible oxidation. So when people say, like, if you're in synthetic organic chemistry lab or inorganic chemistry lab and you do voltammetry and you see a reversible wave, what they actually usually mean is you see a positive and negative peak. We actually also talk about reversible meaning it's Nernstian. But some people use the term more loosely, just meaning that you can drive it forward and drive it backwards. Right? So this is irreversible because as soon as you make R, it decomposes into X or changes into X. Right? Okay, now let's think about this, and we'll just sort of draw all these CVs very qualitatively. So we won't worry about the magnitudes of the currents and things like that. You could do the simulation. You can program all this into the simulator. You can put in multi-step reactions. You can simulate all this. Really easy. In fact, people do that. They'll actually take a voltammogram and then they'll try to figure out a reaction sequence that simulates the voltammogram. Okay. Now, what happens if I change my scan rate and I scan really fast? I'll regain this reverse peak. Why is that? Well, if I make R and then take the R back to O before this reaction has a chance of happening, I'll regain that reverse peak. Okay. And of course, you'll see something between those two limits depending on scan rate. So the scan rate dependence can be used to figure out the kinetics of a chemical reaction. So the kinetics of the chemical reaction are encoded in the scan rate dependence of this voltammetry. So in fact, you can simulate this sort of thing. So you might see a whole family of curves, right? With different amounts of, if I normalize that, normalize the peak current, right? With different amounts of return wave depending on the kinetics of this reaction. And depending on the ratio of Kf and Kb. Because if you remember, K, the equilibrium constant for this reaction is Kf over Kb. Let's do another example.
Quick question.
Yes?
So why doesn't the peak current amplitude change in this case?
Because I normalized all to the, it does change.
Okay.
I said, that's why I said we're just going to like,
Normalize.
you know, I over IP or something like
Okay.
that, just to make it simple for our client.
Thanks.
Good, thanks for clarifying that, yep.
This might be along the same lines, but in the last lecture, you talked about how at faster scan rates, it'll kind of condense closer to the charging clocks.
So yeah, we can go with that. So what happens, if I think about current and potential, and I think about my background non-Faraday capacitor, right? The current for the capacitor, if I'm just doing non-Faraday chemistry, do you remember what the charging current is? It's the scan rate times the capacitance, right? And so what does that mean? So if I increase the scan rate, right, I'm just going to see larger and larger scanning boxes, right? So this is increasing the scan rate, right? And it goes linearly with the scan rate. But the peak current for a Faradaic process is proportional to the scan rate to the 1/2. So what that means is that this capacitive current grows faster with scan rate than the peak current does. So as an example, I might measure if I scan very slowly. If I scan very slowly, I might have a small capacitive current and a well-defined peak, okay? There's my capacitive current, right? But if I scan very fast, and I normalize, let's do I over IP again, right? I might see something that looks like this, okay? Because my capacitance current just grew a lot faster than my peak current did. Because one goes linearly with scan grade, the other goes to the 1/2. Because one's diffusion controlled and one is not diffusion controlled, right? There's nothing diffusing in a non-Faraday reaction. So another type of reaction is called a catalytic reaction. And this is an EC prime. So imagine you have O plus some electrons goes to R. And then I can have that R react with some species Z with some rate constant, K prime, we'll call that forward rate constant. We'll assume it's irreversible. There's no significant backwards component. Goes back to O plus species Y. So what have I done? Well, I've reduced O to make R, right? Then R has gone on and reduced Z to make I and give me O back. So what has happened is basically the OR couple, redox couple, is a catalyst for the ZY redox couple. So what this is saying, like in principle, Z could just get reduced directly on the electrode, but that kinetics is not fast. Those kinetics are not fast, right? So the mechanism first is to reduce O to R, and then that is further reacted homogeneously in solution, right? This is the E step, this is the C step, to make Y. And so an example of this that I like is this sort of so-called Dan Du Bois catalyst. So he's this researcher at Canada now. I think he's retired now. But he developed these really nice nickel phosphine. And there's some R stuff over here. I'll just do the part I care about. R stuff, okay. These nickel phosphine catalysts that actually have this pendant amine group. There's some more R stuff up here. And that pendant amine group stabilizes, just so I can draw this nicer, stabilizes a metal hydride on the nickel species. And this, actually I don't think it works like that. I think there's a lone pair here or something. That's embarrassing. Anyways, so this, this species here stabilizes or modulates the energy and the kinetics of forming this metal hydride, which is an intermediate in making H2. So in principle, you could take protons, so O would be a proton, and you could reduce it to make H2 on the electrode, but it's too slow. But you can reduce this catalyst, which can then react with protons to make H2. That's why it's a catalyst. That's an example of an electrocatalytic reaction. What you see in the voltammetry, just as an example, I, E. So if you have, if this step is slow, so if K prime is really slow, you just get a normal voltammogram, right? Or say there's no Z. Say if I have no Z in solution, this reaction can't happen, right? And so I just get a normal voltammogram. If I add Z, what will happen is I'll get a voltammogram that actually looks like this. If my kinetics are fast. And what's happening is as soon as I start to make R, right? As soon as I start to make R, it reacts with Z to give me Y back. I never run out of O because I'm regenerating the O at a fast rate with Z. And then I get to a limiting current that's actually set by how much Z, how fast Z can diffuse in from the electrolyte. Okay? So we could go through all limiting cases and we could describe this analytically. There's actually fairly straightforward to derive expressions for the limiting currents, and from the limiting currents and the dependence on the concentrations, you can actually quantitatively extract a rate constant for this catalytic reaction. Yeah, that's probably right. The limiting current is going to depend on K prime and Z. Yeah, because you're going to set R, so you're kind of setting the concentration of R by this electrochemical step, and then it's the rate, the maximum rate you can achieve is going to be given by how much Z you can deliver, so the diffusion of Z to the reaction zone near the electrode, and the rate at which it reacts. The point is, you can take any combination of C's and E's. The simple ones have all been derived, so you can look up the equations that govern the way the curves look. But practically these days, you can take any combination, plug it into a simulator, and simulate what the curves should look like, and actually fit. You can even do the reverse and fit your data based on a model, a simulated model. And you can extract rate constants and things like that. Good? So the last one I want to talk about, EE reaction. And we talked about this a little bit before. So what's an EE reaction? What type of reaction is that?
2 electron transfer.
Okay, it's effectively a 2 electron transfer, right? But it's going to be 1 electron at a time, right? And it's going to have some E naught. And then B is going to be able to receive another electron. And it's going to have a second E naught. Okay? So they're individual electron transfer steps. These are nicely illustrated in chapter 12 of Barton Faulkner for as a function of E1 minus E2, the difference between these two. The simple case is where they're well separated, right? So this is E naught 1, E naught 2. So E naught 2 in this case is, let's say, much more positive than E naught 1 if it's on IUPAC scale, right? And then the question is, what happens when these things are very similar to each other? Okay. And the key is that when, for example, this is E naught 1 is much greater than E naught 2. This is a positive, right? Much smaller, it's more negative, right? Now, what if it's the other way around? So what if E1 is more positive than E2? Here it is. It's a very nice table. You can see too for our virtual audience. There it is, chapter 12. It shows how these things change. And you can see this is the case we started with here. And as you go back, what you find is you get a sharper peak, a bigger peak, and a slightly shifted peak, but only one peak. and this is the way to think about this, is as soon as I start doing any chemistry at E naught 1, it's immediately made into, the second reaction immediately occurs. Okay, good. So let's see here. Let's talk maybe briefly about rotating disk voltammetry. Rotating disk. Voltammetry. And so this is one of so-called hydrodynamic methods. Hydrodynamic means we are flowing the electrolyte, right? So dynamic, hydro, flowing the electrolyte. And the advantage is we obtain steady state, fast, and we control mass transport. And specifically, a rotating disk electrode is exactly what it sounds like. You have a shaft. You have your active electrode at the bottom of the shaft. And it has a sheath. Okay, so this is the sheath. It's an insulator. And this is your electrode. And if I did this is a side view. If I did a bottom view, then it would just look like a circle with my electrode in the bottom, okay? And then what I'm going to do is I'm going to rotate this shaft around this axis here, okay? So we rotate. Rotating disk electrode. Pretty simple. Okay. And then what happens, here's our electrode, right? Our insulator that's rotating. This is rotating. And the friction, right? There's going to be the surface is rotating, and there's some frictional force between the rotating surface and the liquid, right? Just like you move your hand through water, you drag the water with you a little bit because of the frictional force. And so what happens is you actually drag the electrolyte and cause it to flow over the surface due to that frictional force. And if I look at the flow pattern of the electrolyte actually looks like this. So you basically have electrolyte coming from the bulk and getting pushed out across your electrode. That's what the flow pattern looks like. This would be R going out and Y going out. And you can solve this, okay? You can solve a set of equations. So Ballard does this. So just how we solved all the other equations, or we set them up, we didn't actually solve them really, except at the very beginning. We need boundary conditions, right? We need some sort of dependencies on the variables we're going to adjust experimentally. So this is a convective diffusion problem. We have both convective flow and we have diffusion of a species. And so the current turns out is given by this equation. NFA, so that's always in there. Diffusion coefficient to the 2/3 power, the angular frequency to the 1/2, the scan rate to -1/6 times CO star minus CO y equals 0. Okay, so this is just some equation that comes out of this, or we can write, this will describe the curve, right? The curve depending on the bulk concentration and the surface concentration. And if it's Nernstian, we can use the Nernst equation to set the surface concentration. If it's not Nernstian, it gets even more complicated. But if you set this to 0, so the surface concentration to 0, we get to the limiting current And that's kind of what people usually analyze. 0.62 NFA D naught to the 2/3. Angular frequency, so how fast we're rotating, to the 1/2. Scan rate to -1/6 times CO star. So this is the limiting current. And the nice thing about this is you can now directly get, remember before we had this mass transfer coefficient, which was kind of taking the place of the diffusion coefficient, but it was related to the stagnant layer width and all that kind of sort of hand-waving stuff we did in chapter 1. Now you don't have that. This is a more rigorous solution to the convective diffusion equation. But otherwise, it's very similar to that response. If you think about this, what we get, I, the current I, the limiting current, should just depend on rotation rate. If you have an ideal system, right? So I didn't write a rate constant in here anywhere so far, right? So if I have a Nernstian system, the limiting current just is going to depend on the rotation rate. Okay, so what people measure, if I plot I versus the rotation rate, you know, if it was ideal, it should just go up. Right? It was the rotation rate. But at some point, it's going to start curving over. Right? And this is going to tell me that the kinetics are limiting. Because if you think about this, I'm scanning faster and faster and faster. As I scan faster, I'm delivering more species to the electrode surface, but my current's not going up anymore. That means it's no longer controlled by mass transport. Here it's controlled by mass transport. Here it's controlled by kinetics of the reaction. And so this actually maps this all out. This is why rotating disk voltammetry is really useful, because you can actually map all these things out. You plot 1 over I versus omega to the 1/2 for different potentials. You can think about this here. You get, so this is called a Kuchke-Levitz plot, or Kuchecki-Levitz actually. Kuchecki, I think is how you pronounce it. I don't know. Kuchecki-Levitz. What you see is you can actually plot this as a function of potential. E1, E2, E3. And then if you extrapolate back to infinite rotation rate, so where omega the 1/2 goes to 0, what that tells you is 1 over something called IK. And that 1 over IK depends on the potential. That's the kinetic current. So what that is it's the current you would measure if mass transport was infinitely fast. The basic idea here is you make measurements over a variety of rates, and those rotation rates have each rotation rate, there's a certain overpotential for driving mass transport, and there's a certain overpotential for driving the kinetics. And by changing how fast you rotate, you can actually figure out which proportion is for kinetics and which proportion is for mass transport. And what we do is then we take that dependency, there's an equation called the Kuchecki-Levitz equation, and this is what we're plotting here. And if you extrapolate the data you have to a point where mass transfer is infinitely fast, then you have data that just tells you the kinetics. And that's often something you really want to know. So this is how you understand electrochemical kinetics in the absence of mass transfer effects. So for example, when we did hydrogen evolution in strong acid, we didn't care because there's so many protons around, mass transport wasn't an issue. But if you're doing electrochemical kinetics, for example, of reducing O2, which is dissolved in liquid, for like a fuel cell, the concentration of O2 is very low. So mass transfer is never not important. So you have to do rotating disk electrode experiments to take out the effect of mass transport just to study electron transfer kinetics. So you rotate, you change how fast you rotate, that changes how good the mass transport is, and you fit that to equation to extrapolate to where mass transport doesn't matter. That's really the scope of it. There's other cool experiments you can do with a rotating disc electrode. Just again show, this is called a ring disc. This is a rotating disc, and the other thing you can do is you can put an insulator. So this is metal. This would be like plastic. And then say you put a ring here. That's say metal again, right? Or to be more specific, it might be platinum and platinum, okay? And then what you can do is you can do some reaction here. Say you go O plus an electron goes to R here, and then you can do another reaction. You can take O or R and go back to O plus an electron here. So these two can be at different potentials. And for example, why you might do this? Say you're looking at oxygen reduction, okay? You're taking O2, can either be reduced to water, H2O, or it can be reduced to hydrogen peroxide, H2O2. Water is a 4-electron pathway, hydrogen peroxide is a 2-electron pathway. What you can do is you can do the reaction here, make the reduction product, water or hydrogen peroxide, and then here you can sense how much of that reduction product was hydrogen peroxide. Because hydrogen peroxide you can further reduce or oxidize back to oxygen. So you basically can sense your product at a different electrode than you made it at. And you can do a lot of valuable experiments this day. It's called rotating ring disc electrode. So these two potentials can be different from each other, and you can do different reactions there. So you can also look at like Faraday efficiency, so-called Faraday efficiency. Like say you have O plus electron goes to R, but there's a background reaction that's some other reaction you don't care about. And you want to know like what fraction of my current is actually making the thing I want it to make. And you can go and say, well, okay, I'm going to reduce it back to O. And you calibrate your rotating ring disc system, and you can actually do that experiment. So what you usually do is you take something that you know the Faraday efficiency is 1, like ferrocene, ferrocenium, and you reduce it here, and then you see like what fraction of the stuff you reduced you get to oxidize back, and say you only collect like say 10% of it. Because you know some of it will diffuse away, you won't be able to collect all of it, right? You only capture a fraction of it. And you say, okay, well, I know for a system that I understand really well that is completely reversible that I get 10%. And then you go characterize your unknown system and say, oh, in this unknown system I only get 5%, so therefore the Faraday efficiency is only 50%, because it's 50% of the ideal system.